Okay. We are very close to the final project, which would be integration of whatever I've taught. So about regression. Regression is a very huge topic. It's a major part of machine learning, and there are some basic uh, techniques, methods, and a basic thing syntax that I plan to teach you guys. And after you get an idea of how it is all implemented, you can start working on you know exploring different methods that I'll let you know, and then we can implement those methods and find a project. And there is also one concept that I'll teach you, which is hyperparameter optimization. And hyperparameter optimization is tuning those parameters to get the best, equation which fits the model. By best, I don't mean overfitting, but just a good fit. And uh, the material has been shared with you all already. So I'll just go through the, the basics of regression, and then I'll teach you the syntax, which is actually pretty much similar for most of them. So the uh, first way would be to import all the libraries, which I've done here. So just import all of them at once. You can also do step by step, but actually people tend to forget importing libraries if it's not done for the first time. So yeah. Now let's start with linear regression. So linear regression can be understood as fitting a curve. That is what regression can be understood in layman terms. And as you can see from linear regression, that it's a basic linear equation, y equal to x plus c, where there is a constant, and this constant can be the constants can have two parts. One is error and one is the intercept. And error is a very important term in machine learning because you tend to understand how is your model learning with respect to the data and the parameters you have given. So when I say hyperparameters, I mean P, E, and B star. So these are the hyperparameters. These are a part of equation which is not controlled totally by you, but by the algorithm itself. So this is hyperparameters. When I say features, it means data variables like x1, x2, x3. And when I say target, it means the output, which is y in this case. And learn the basics of regression through this link. Now, you can see here this regression has two parts. One is classification, and one is regression. Classification is based on uh, creating classes, creating clusters of the points based on their nature and position on the graph. So when I say if it had been a classification problem, there would have been two clusters of points in in this data set. And when I say regression, it can be a line which segregates the data, a line which may fit the data. So this is the difference between classification and regression. Classification is used on historical data, and regression is used to forecast the data using historical data. This is similar to, so basically, machine learning has two methods, two types of learning, supervised and unsupervised. and yeah, supervised and unsupervised. Supervised is a type of learning where you have the past data and then you try to create clusters, and unsupervised is when you're trying to forecast the data and using the previous historical data. So you must be knowing the production forecast that we do use in softwares. It's a type of okay. This production forecast, this type of unsupervised learning, where we try to use historical data and understand the nature of growth. Now we try to understand the syntax and how linear regression works. We try to explain you basic algorithm for which you can train a model. And I haven't kept all the models in this. There's a lot of other models when you start learning the statistics and you know uh, the complex algorithms. So I've taught you. I took some. I picked a really good algorithms which will help you learn the syntax and also give you exposure to different kind of methods that are being used. There are many methods: linear regression, ensemble methods, bagging, boosting, and all that. So I've covered that so that you can have exposure to what's happening. Now I've created these data sets of 6 points, which I'll be using to create uh, on which I'll be using linear regression model to uh, to implement. So let me import the library, then create the data set. So now you can see the X has these 6 points, Y has these points. You can check X here, and then check Y here. So you can see you can see how it's now the data set. Now, in machine learning, we use sklearn linear model. This is the library. This is a sub-library from which we import this tool. So here is it's already already uh, downloaded the package. So you can see sklearn has a lot of sub-libraries, and we get those tools from those sub-libraries by calling sklearn and the sub-library. So here from SK linear model, we import linear regression. We we import the we import the regression method in this variable named model. So what happened till now is you got the equation from this library, which doesn't have any values as of now, and then you put this equation in this variable called model. Okay, and now using this function dot fit, you try to fit the data in that equation, and now the learning happens. So this model is trying to fit the data x and y in this linear regression equation. So let's do this. You can also use this method where you are directly using linear regression instead of model. Like you can use linear regression directly dot linear regression function, and then you fit the model directly. Now, the important part of machine learning is after you have trained the model, you need to understand how is that model better than the other ones you have, implemented, because you'll not be
Excuse me,
using one
sir.
algorithm. Yeah, tell me.
Sir, actually, the site about the supervised and versus unsupervised learning is presented, not the notebook, actually.
Oh, okay. could have told me that earlier. Uh, okay. Is this visible now?
Yes, sir, it's now visible.
Okay, great. So when I say linear regression being used on 6 points we already know, it's supervised learning. So we'll train the model and then we'll try to predict the values using the model. So, uh, okay. So we got the values of X and Y, which we have feeded here using an array. And using sklearn linear model, we import linear regression tool and we we import the equation in this variable named model. We fit the data X and Y. This is where the training happens, where model is trying to fit according to the data and the hyperparameters are changing according to the data feeded. Now after this, yeah, so I was about the scores and errors, which are important part of machine learning, because you won't be knowing which model or which method or which equation is the best for your data. So what happens is first you try to finalize the method. Okay, we need to have regression. Okay, what kind of regression? Linear, logistic, Bayesian, and other 5 6 methods. And then you choose 2 or 3 depending upon what's the data size, what's the frequency, and if if you need a more complex model to understand the data. And after you have chosen those 2 3 models, you try to implement them, and then after you have implemented, you try to compare the accuracy scores. So there are many types of scores in machine learning. You have generalization score, memorization score, R square, square mean square root error, absolute means absolute square error. And there are many ones. So there are some basics ones that I have gone through and I use them. You can use many of them to compare and finalize that and be sure that okay, this is good enough. Now I'm trying to explain you the equation that we have used and what are the variables that we got after fitting the model. So in this you can see R square, which is score of the model that we have fitted. And this is the coefficient of determination as I've written, which is 0.71. So this score is actually 71%, which is good enough. Any score above 70, well, it's not that good of a fit. But yeah, for linear regression, uh, as it's a very basic model, it will just have a limitation to accuracy unless the data is actually linear. And so we got the score, which is accuracy. And now, as I said, it's in the form of B naught, B1, X1, B2, X2. You can also get the intercepts, coefficient, and slope, and everything you want in this equation. So this I have done using these functions, coefficient, intercept of model, which was trained here. And you can get the whole equation actually. So this was linear regression. Now we come to logistic regression. The thing that logistic regression, which makes it a uh, better model than a better option than linear, is that it fixes all the values between 0 to 1, and this is done using this function named 1/1 plus e power minus x. So this function we use during IIT JEE also, if you remember, it brings down the whole value from 0 to 1. And that's the specialty about logistic regression. So we feed all the x values in this function, and uh, whatever values we get as an output, we try to train those values against y. I hope you got my point. So, and this function is called sigmoid function, which is used in logistic. So in logistic function, and there are a lot of tuning and changes that have been done till now in logistic regression. And if you try to understand the modern ones, like the updated ones, there are a lot of other changes. But this is the basic one which we start with. And so now we run this model uh, on the well data that we have used before. So what I've done is that I've imported those wells. And if you remember pre-processing class, I have filtered and cleaned the data, replaced the values with median, mean, remove the outliers, and I've actually pre-processed the data. So what I want is that when this class is done, you guys can actually do the pre-processing by yourself and then train the model. So what will you understand is that in this one, I haven't done any pre-processing. So obviously the accuracy won't be good because you have so many outliers, missing values, and a very raw data. When you pre-process the data, you'll see how the model is training better than a non-pre-processed data. This is an exercise for you where you can start you can run a model on a pre-processed data after all the pre-processing you have done, and then you can train exactly the same model, and then you'll understand, okay, this is the difference in accuracy I'm getting by pre-processing data, by scaling the data, and normalizing the values. So okay, now I've told you a kind of homework, and there'll be much more stuff to do today before final project starts. So this all I've done in pre-processing also. And if you find a keyword which is actually not known to you, or you are confused about that, just Google it. So uh, if you find difficult to understand what is PD contact, so I can just tell you that PD is pandas library, and concat by definition is merging the values uh, in column manner, which is column because this is actually equal to zero. And if you find it difficult, you can just, really, it's very easy. I'm teaching you this because it will be helpful to you in long run to learn this. So here actually you can see PD concat definition, just copy and Google it. And then I changed the val variable to 012 and change the RT log data in log 10 base. And this is all I've done before. I'm just going through this to make you familiar. I've changed the FACI labels 1, 2, 3, 4. I've changed the index from 0, 1, 2, 3 to depth. So you can see from here, you can see data again. So index is depth. I've changed the FACI labels. And now you'll understand why did I change the FACI labels from these variable SHU and like from string to integer. Now I can understand why I did that, because now you need to run these variables through equation. Now there is another method where you don't need to convert it, but for you to have better understanding, it's better if I converted those variables into numbers, because now you can actually fit the data and get output an equation using numbers. We can also have a look at X and Y now. Oh, this is okay, capital X. This is our feature, And now we can have a look at the variable. So these are our variable. And I have taught you before, why are we training? Why are we splitting the data into testing and training? And I took test size as 0.3. It can vary, and it can be, it has to be something above 60. The training size has to be above 60, 70, which is good enough. And so now we can see the dimensions of the training set and the testing set. Now I'll give you a flow of what happens actually. Now you pre-process the data, you split the data into training and testing. You import the model, you fit the model into the data, and this data would be training data. Okay, you're trying to run the model on training data. When your model is trained, you use that equation, trained model to run on testing data, so that this testing data is new to the model, right? So it will be exercise to see how accurate is our model, and then we can understand the error, the how good is actually our model running, and we can compare other variables to see how good is our model among the ones we have chosen. So I've done what exactly I've told you. I imported logistic regression, and this you can see C equal to 12. So there are a lot of hyperparameters in the models that I'll be training you. Now C is called penalty function in logistic regression. And penalty function is actually something related to error function where it's trying to learn from error. Now these methods can be really complex and complicated from linear and logistic regression. They'll have a lot of statistics, hyperparameters, and algorithms. I've just told you how logistic regression is using the sigmoid function, but if you see the real logistic regression equation, it will be very complicated. And I'm not telling you not to learn, but actually it's not what you should focus on if you're just trying to learn the application of machine learning, which is my aim in this workshop. But of course, you can just go on any site or Google it or go to WC schools and learn what's the equation and how it's working. uh, and then I use this classifier to fit the model of X train and Y train, which was splitted here. And after it's done, I try to find coefficient and intercept. So actually, this part is not necessary. It's just to uh, show you what are the variables that we get while training. So these are the uh, variables of the equation we got. And you can ignore this as just a warning function, or sometimes it's that, oh, we have loaded this. You can learn more about this and this, okay, about this and these lines. So this is something from library. You can ignore them, and it doesn't matter much. Now you see they gave this warning, and then they also give the source to learn this. Now you can see how optimization problem works using these equations. It's complicated. So let's not go there. And now, so I told you we train the model and then we test the model, the learned model on the testing data. So we use that functionality here. We got the trained classifier model, and you can also check through this way. So you see it's a logistic regression model with equal to 12 and a fitted data of X chain and Y chain here. And then we predict the values of X test using this model, and we feed the values in prediction variable. Uh, this is predicting y values, which we already have using x values. And what will happen after this is when we get the predicted y values, y test values, we'll try to compare it with y original value. So now we have predicted values and y original. So it'll be easy for us to compare because we have both the values now. So we predict the model and we feed the data. Now there are two types of scores, as I've said before, which I use. It's a kind of accuracy score, generalization and memorization. So memorization score is a kind of accuracy score which tells how the model has, you know, performed with training set. And generalization score is a kind of accuracy score which tells how has model performed in testing data set. So sometimes we'll see with the problem how it matters to us. Now you see memorization score has to be always greater than generalization score. This is because you have more data set. Your model is having both the values of y train and x train. So obviously it'll have a better learning. And generalization score is on testing data, which is new data. And that's why it has to be less because your model is not aware of the data set now. And there is also something called F1 score. So there are many types of score: precision score, recall score, F1 score, and you can actually use all of them to find the difference because each type of score gives you a different perspective of the model that you have trained. So we can use that. Here we tried predicting the F1 score and average all the Y values and then compared it. So there are different type of scores you can get. And and now we see the confusion matrix. So we have names of the classification here. And now we create a confusion matrix where we have Y train, which is the original Y value, and then the predicted Y train values. We create a heat map. We give all the hyperparameter values, CF matrix, and all kind of variables that I wanted. You can get the definition of, I've told you about ANET, FMT, XTech, YTech, size. This is the gradient in color that I want. So you can understand this, and then PLT show to get the graph. I don't know why it's not showing completely. Okay. I will. Okay, I don't know why there is a cut here. It shouldn't have happened, but anyway, you can see it's kind of 720 the value, and I'll explain you what the matrix is about. So you can see CBSSU and the classes, the faces here and the faces this way, and you can see there is a matrix with numbers and giving a kind of relation between predicted and actual values. So if you see SH here, it's 720, it means there were 720 data points which had SH value both in predicted and actual data, which is good for us because you can see SH values is 181 and 720. So around 80% of the data had actual values which are matching with the predicted values. And similarly with 552, 511 and CB, it was CB had different values here, you can see. It didn't have a good learning because CB cross CB should have been a major chunk of values. So You have just learned now to, pre-process the data, classify the data, split the data here, import the model, fit the data, predict the values, find the accuracy scores, and generate this matrix to understand how the values have performed with respect to the original data. Now, there are different kind of techniques. Okay, you can have linear, logistic, rate, lasso, polynomial, Bayesian. So we have seen linear. Polynomial is complex version of linear where we can have cubic, quadratic, and polynomial equations as the fitting curve. Logistic, we saw the sigmoid function. Ridge and Raj lasso are extension of logistic function. The difference is between how they are interpreting the errors among these values. So Ridge uses a penalty function called as L1, and Lasso uses a penalty function as L2. Well, you don't need to know what is L1 and L2 and what's the equation, but they have different learning with respect to the errors we get in the function. And Bayesian linear equation is extension of, again, linear regression, but it uses Bayesian statistics and Bayesian learning, which is a different equation than the normal linear equation. So you don't need to apply all of them. So what happens normally is that we use logistic or linear regression to find the first base model. That's because we use the simplest of all models to get, okay, a linear is 70%, and this is the error, and these are the predicted values. So we now know the complex models that we'll use in future should have at least 70% accuracy and these predicted values. So regression in general, and that too logistic and linear, are used as base models, not the final options to predict the values. As you learn more complex models, you'll see that you won't be focusing on getting the best linear model or logistic model, but it's just a base model to understand, okay, this is a standard and now we need to get more accuracy. And the best thing about these models is that they are very interpretable. You can actually see how linear equations are working and what's the difference. How are these equations being generated? What are the coefficient, intercept, and slope? And this is the difference with other models, that as these models get complex, their interpretability decreases. We actually, at a certain point, really don't understand how how are these complex models working, because there are so many parameters and a complex equation and a lot of statistics used that we actually are unaware of how these models are actually working mathematically to train the data. So this is a compromise that we have in machine learning, that when we tend to use complex models, we actually lose the interpretability of the model. So you need to have a good experience and uh, a good learning and thorough experience with models so that you don't have interpretability issues. And now we go to random forest regression, which is a type of ensemble method. As I've told you before, there are many types of methods that we'll be using, and I took one of each, and I'm not teaching you all of them. So that's a homework for you, that now you can learn about list, lasso, polynomial, and see what's ensemble methods, what's more there other than random forest. Ensemble methods, as you can see, I've given a definition. They use different kind of decisions uh, to predict the model. So to give you a better idea, these are the ensemble methods. KNN, which is K, nearest neighbor, knife base, support vector machine, and decision tree. And random forest regression is complex upgradation of decision tree. And these are ensemble methods where we use accurate predictions than individual models. The thing with linear regression was that we are using this single equation to decide the data. Now, what decision tree does is that it will give a lot of different equations, and then on the basis of the accuracy, it will decide which one is best to go for. So that is ensemble methods. There are two types of ensemble methods: bagging, bootstrap aggregation, which is bagging generally we say it, and then boosting. Now, boosting, you have written the definition. It uses group of algorithms to utilize the weighted average to make weak learners into strong learners. Now, what happens is sometimes is that suppose for example, you have this equation, right? And suppose B naught is not contributing that effectively. So these methods give a good training to this variable and give a better weightage to it so that it can actually have a uh, better learning as a whole equation to give a better accuracy. And and the bagging, it actually removes the weak learners and gives you a better strong equation, that is bagging and boosting. Now, this is what I was saying about random forest. So you see here we have cluster of decisions happening. These are called trees, decision trees, and you can see how many, there are so many decision trees. This whole is first decision tree, and then these two, then these. So it's 4, 5, 6, 7, and then 3 from here. So that is around 13, then 14, then 15. So 15 decision trees, 15 kind of experimental algorithms to decide, okay, which one is good one. And how this tree works is that suppose we have 600 trees here, right? Now we have to predict values, suppose, okay, and we have the target values from 1 to 600. So decision tree works this way. So suppose we have value 2. So it will go to this, then 2, is it true or false? Okay, this is false. So then we have another 2 variables. So it works on predicted values and it segregates the data that way. And then using the error we get using the predicted and actual values, it takes average of all that, and then we get the prediction. Now, it must be really confusing for you to understand what I'm saying or how it's working. So best way is to actually learn the model step by step and go to some very detailed source to understand random forest. Random forest is a very, very important method in machine learning. It's a complex method, and it's kind of between good interpretability and good complexity model. It's not too complex, and it doesn't loses a lot of interpretability. We can still understand how decision trees are working, but it depends on the number of decision trees you are using. You can also actually decide in advanced stages that how many trees you want to use. So this has 600 trees, which is a lot of trees to decide. Now, so we go to how we can use random forest classification here. And, and after that, I'll teach you support vector machine and how to train support vector machine. And that is the end of today. We use random forest classifier, we have imported. We have imported we have actually fixed the hyperparameters. Now, number of estimators are number of chances we give to a data point for average prediction. Maximum depth is the depth of tree. What I mean by that is, so this is first level. So this is depth 1. This is depth 2. Then third decision is depth 3. depth 4, and there is one more depth 5, and then we get the prediction. Then we get the prediction. So you're actually deciding the complexity of the tree using estimators, maximum depth, criterion, which is actually a kind of decision algorithm, and n jobs. These are different hyperparameters which you need to understand by actually experimenting. So now what you can do is you can create another model which has n jobs equal to 5, 10, 15, and then you can see how the prediction ones are changing. So that's the advanced stage where we use hyperparameter optimization. Where we give multiple values to these hyperparameters, and then we get the best model after training, and then we decide, okay, these are the hyperparameters that I want. So now you have free forest model with all these hyperparameters, and then you fit the data into X-chain and Y-chain. After you fit the data, you predict the X test values into Y-pred. Y-pred is Y prediction. And then you can calculate the accuracy scores from here now. So see, it's 87, 89, which is really good accuracy score. Not the best, but better than what we got in linear, which is 78, 77 kind of. So it's a 10% increase on what accuracy score we were getting. Similarly, you can get compare reference scores, and you can learn more about random forest from here, this equation, this site from Medium. And another interesting method that I found is support vector machine. And also a very easy, cool method is KNN. KNN is also a very, are you able to see my screen?
Yes, sir, it's
Uh,
visible.
about K nearest neighbor?
Yes, sir.
Okay. So yeah, one method that I didn't include because of the time constraint is KNN actually. And KNN is a very interesting method. It has a very easy algorithm that is being used. I can just show you from the diagram actually. So what KNN does is it segregates the data. It takes the average of all these points and then it calculates the distance from them. And based on the distance, it creates clusters. So that is KNN. That is, it's one of the most simplest algorithm to understand, and it has a very great interpretability. You just give the distance size like 1, 2, 3, 4, 5, and then on the base of average distance, it clusters the data. So that's KNN. And a similar but a complex algorithm is SVM. What it does is, so suppose we have two cluster of data points, and there can be infinite lines which can actually define the cluster of these data points. You can see you can create infinite lines in between, which can create a segregation and make you believe like, okay, these are the lines which are segregating. So all of them are good, all of them are classifiers. But what SVM does is it takes the line which has farthest distance from the closest points. So you understood the logic. It takes the farthest line from the closest points in those clusters, and that is your optimal hyperplane or optimal hyperline. So this distance is equal to this distance, and these are the closest points of the cluster. And this is, you're trying to create a line which has maximum distance from these two, equal maximum distance. So this is SVM algorithm which uses this logic to get this hyperplane. And then it finalizes like, okay, this is the optimal hyperplane which is segregating or clustering the data. And I'll also teach you now what is hyperparameter optimization. So you must be always like, okay, now we have to create another model which has an estimator as 150, 200, and then train all those three models and then compare and then get the best model, right? So this is where hyperparameter optimization can help you. So from SK, so this is the tool we use for hyperparameter optimization, so model selection in sklearn. And I told you, right, I give range to these variables. So kernel, I give RBF, I give, and so what is happening is I'm giving a range of values to these hyperparameters so that when I try to optimize these parameters, I get the best values from these range. I'm giving gamma around 6, 7 values. I'm giving polynomial, linear, all these values, and degree, which is a variable, which is a hyperparameter in SVM. And now I try to find the best model with best hyperparameter. So it's on this. Now it's learning. You can see how the model is learning now. It's trying to, it has 205 combinations of model which it's learning together. And these 205 various models are from these ranges that we have taken. So I hope you got the point here that I'm trying to create many models, and then I'm running those models on these data sets. And then I'm trying to find the best estimator from all the 205 models that we have got. And now you can see this is a model where gamma is equal to 1, C is 0.1, and kernel is RBF. Now it'll keep saying like, so C is now 10, gamma is 0.01, kernel is RBF. So it's almost on C equal to 100 and gamma is 0.1. So it'll take time because you're learning 205 models, and you can see as the model is getting complex, the time to learn is also getting more. And this star shows that it's still learning. So let's give it some time, and I'll explain you the the, the syntax that I'm using after this. So bet params, which is get the best parameters of SVC model that we are using, and which we have various 205 tuned hyperparameters. Then after getting the best parameter model, we store this model into SVC mode, which is a support vector model, and we store the best parameter so that, because now we know this is the best model we need to run on. And then using this model, we try to predict the scores, and F1 score, we try to fit the data into Xtrain now, and then uh, we compare the predicted values with the actual values. And then we create a confusion matrix to see how these values are, uh, how accurate are these values with respect to the original values. Yeah, it's taking a lot of time. And that's the thing with these models, that as you try to increase the parameters, make it more, versatile, it tends to take a lot of computational power. Now, that's where Python is kind of slow. This is what I was saying, that Python is a slow language because it uses a lot of background libraries, and it has a complex uh, background. But that's not the case with C++. That's why all the reservoir simulators are still made on Fortran and C++ with a little bit use of MATLAB. And That's why we haven't built any reservoir simulator in Python, because you can say it's a small model, but it's still taking a lot of time to compute. Now it's taking almost around minutes to train a model. So you can see if you feed so many terabytes of data for it to learn, it will take a lot of time. Now, you can say that I have low computational power, but still, if you run a reservoir simulation model in MATLAB, it could have been done by now. If you have like this amount of complexity with data, which is very low. Now, I'll leave it at this point because I'm not sure how much time it take. I don't remember. But as soon as this model is trained, you can get the best parameters. You can find the score, and I'm thinking that the score will be better than logistic regression because we have tuned the parameters, and we have used the best optimized model in SVC. And if it doesn't happen, it means random forest is a much better model for this kind of data than SVC, because we have actually not hyperparameter. We haven't tuned the hyperparameters. We just have one model, and we got accuracy of 89 to 88. We focus on 88, which is the generalization score. And now uh, uh, let this be exercise for you guys, because it's taking a lot of time and I don't want to waste the time. Now you can run this code and see the best parameters out of all these, and you can check the accuracy and generalization score. You can fit the data, and you can see the confusion matrix. I am thinking it'll be better than random forest, but let's see. Uh, So I've shown you around four models now: logistic, linear, random forest, and SVM. There are a lot of other models, algorithms, and a lot of other methods that we use in machine learning to train the model. And I have taught you the of the basics of all the syntax methods that you'll be needing. And again, I'm saying this, you have to know what is kernel, what is gamma, and this has to be done by you Googling it and finding sources or reading it from books, whichever way is comfortable with you. You need to know what is F1 score, why am I using F1 score, and why have we used average here? What is memorization, generalization? Even though I have told you, you need to go and see the definition again. What is C, what is penalty, what is, you know, any kind of variable that you find, just Google it. You need to know how to Google and learn from that perspective. So this is it for now. I'll keep looking if the model is trained, and if it's done within the time frame of this workshop, I'll show you the the model. And now we can have any Q&A that you guys have talked about. Any doubts from previous ones or this one? I see. I can see that. Please share the notebook screen. Oh, okay, okay. Any doubts? You can unmute yourself. I think Preet has given the right to unmute. And yeah. And final project will be very similar to this, but we'll be using other algorithms uh, to train all the models and get the accuracy scores, compare them. So that will be our final project. We'll be using the same data that I have given to you before. And final project is more of integration of everything, and uh, applying whatever we have learned and see how actually it's being used in industry. Okay, so about memorization score, Soumya, what happens with machine learning models is that it trains the data and then it compares the predicted values with the actual values, and that is called memorization score. So your model cannot have score equal to one because you your model is not going to have that good of a learning. And if it's one, what I'll tell you is that we get a lot of time one actually. And and that happens because your model is now overfitting. And as soon as you get one, you should be sure that your model is overfitting now. It's not the right model. So you need to change parameters to work on the data pre-processing again and then check again. It cannot be one other set because there will be always a difference between predicted and actual values. That's what machine learning is. In machine learning, you cannot get accuracy of 100% unless the data is very lame, maybe x equal to y kind of equation. Yes, you might get a very close memorization score of one, but again, it cannot be one because this is what is the difference between prediction through model and actual values. The random set is actually based on how randomized data you want. So it actually doesn't matter much if you're trying to just randomize the data. It's not a very important parameter, but you should always keep it around 20 to 40. That's what I keep it for. Uh, and actually, the thing with the random state again is that I told you before, maybe second or third class, that random function is one of the most complex function in computer science history. Even now, it's not accurate. So the more randomized you, the more data randomization you do, it might be at a point where there is no more randomness in the data. So yeah, and actually, Abhirup, you can try to experiment this using different random state. So you can just take random, split the data and randomize it at 1,110 and then see how's the accuracy score. So you can do that. Anything else? Okay, I think there's no more equation. And if you guys have any doubt, please reach out to me via emails. I'll reply to you in a day or two as I get time. And yeah, that's it. And try to, learn by yourself. This is the best way to learn. I can give you directions, but actually not can teach you everything in this workshop. Yeah, so good luck and thank you.
Thank you, sir. And thank you everyone for joining us today. I hope I'll see you all tomorrow again for the last session. Thank you.
Yeah, bye. Thank you.
Bye, sir.
Bye.